As background, as we start Chapter 4, we're going to be doing systems of linear equations, and we're going to be solving them by graphing. So really transfers a lot of what we've learned in Chapter 3 for the beginning of Chapter 4. Now, as background, I've made 3 graphs. And if I were to graph, let's say, a line that looked like so, and then I graphed another line, and it looked like so, you might say they are different graphs, but at this particular point, right here, they are intersecting. Now, remember, there's an infinite number of points along this line and an infinite number of points along this line. But at this point of intersection, there's going to be a common ordered pair. Didn't come out too well, it's supposed to be a y. That is a solution for the red line and this sort of purple line. So it would be a unique solution at that point of intersection. Now, in another scenario, we might have drawn this line, and then when we drew the line of the other equation, it looked like that. Now, as you can tell, these lines are parallel, and will they ever intersect? And the answer is no. So there would never be a common solution for this, so there would be no solution for that one. Now, another scenario might be we draw a line for the first equation, and even though the second equation looked a little different, when we drew the second equation, lo and behold, it was right on top of the first equation. So for all practical purposes, these lines, even though they looked a little different, were in fact the same. So how many solutions would these have? Well, we said there was an infinite number of ordered pairs along a line. So for this one, there would be an infinite number of solutions. So these are the scenarios that are going on, and we're going to look at these systems of linear equations to see if they have that unique point of intersection, or there are no solutions, or there are an infinite number of solutions. Now, as we start it off, they're asking us to determine, is this ordered pair a solution for this system of equations? So, how do we do it? Well, we substitute. We get this x, which is a negative 4, plus a negative 5. Does that equal a negative 9? And the answer is yes. All right, how about this one? A negative 4 minus a minus 5. Notice we have to bring in that negative sign as part of our answer. Now, when we have the, and does that equal 1? Well, when we have the opposite of a negative, these change the signs, and we have 1 equals 1. So this checks. So your answer is this a solution for this system of equations? And the answer is yes. Now, this is what we're going to ask you to do for B, C, and D. Now, I've shown you the method, so as classwork, we may assign these out, or we'll put the answers up here shortly. So for the second one, we just substituted this into the first equation, and that was not a solution. So whether it solves the second one or not doesn't make any difference. This is not a solution. So no, this is not a solution. All right, let's go on to the other two. So substituting, this is going to be an 8. 2 times 4. Now, we change signs here. So 4 plus 4 is 8. So this works for the top one. Now for the bottom one, we have a 4 equals a negative 12. Now the opposite of a negative 4 times a negative 4, well, this gives us a positive 16, and we get then 4 equals 4, and I had to copy that correctly. So for letter C, the answer is yes. Now it's critical, again, as you include this work in your homework log, and then later on your blue sheet, that you write out the example and show the work to arrive at your answer. All right, let's do letter D. Now in example D, we get here a negative 9 equals 9. So that's a no. And here we get a negative 12. This is a negative 3. This is a positive 12. So neither of them work. So for letter D, it said no. So again, we were looking for that unique pair, ordered pair, where they intersected and was a solution for both equations. We had 2 yeses, and as you look at these equations again, you can see that these equations are not the same. Okay, let's go on. Now, these next two are rather a challenge because we are to solve these equations by graphing. Now, when I did this before, I didn't have graph paper, so sketching them really doesn't do a good job. You sort of get an idea if they're going to intersect somewhere. But the use of graph paper, and then you'll be able to use your MathLab graph, which is excellent, will help you with the solving of this. So what we have to do is determine what method we're going to use to solve these. So I think in letter A, we might use the x and y intercept t-chart. And for the second equation, since we're going to end up with fractions, I think we could solve that by slope-intercept. So let's try that and see what comes out. So this is what I have for letter A. I use the x and y intercept t-chart to get my intercepts, and then I solve the second equation for y, and I will use the slope-intercept method to graph. Now, to get a nice straight line, I went over to my x and y intercepts here. So it's over 1 up 4, over 1 up 4, over 1 up 4, so I can get a nice line. So I'm going to sketch that in. There we go. Now we're going to do this one. So for this one, I put my dot on -1, and my slope is negative, so over 2 up 5. And notice we have a spot of intersection right there. But I'm going to put my line in there. And it will look something like so. Now, your math lab is going to be much more accurate than this. So what do we have? Well, again, you have to draw the graph accurately and then pick out your ordered pair. So it looks like -2 and then up 1, 2, 3, 4 is the solution for both of these. Now, in MathLab, again, you're going to get a good reading, but it never hurts to check these. If you put these values into these equations, you see it makes both of them correct. Okay, let's do letter B. Now again, we're going to get fractions here. So I will solve this one for y, and this one I will use the x and y intercepts. Okay, so what I have here is my slope-intercept form. Now it's giving me an 11, and I don't have 11 spaces. So what I'll have to do is make each of these 2. This will be 2, 4, 6, 8, 10, 12. So I can do an 11. And I need a 14. So let me sketch these in. In MathLab, you're going to have a graph that will accommodate what you're doing there. So after careful graphing, let me show you what I've done. Y equals a positive 11 here. So 2, 4, 6, 8, 10, 11, about halfway up. And then my slope was a -2, well, -3 over 2. So I went 2 this way and up 1.5, which is 3. And there's my line. Now for this one, it's 0, 7. So I went up 1, 2, 4, 6, 7. And then 14, this was even, 2, 4, 6, 8, 10, 12, 14. And look at where it's going to intersect. Now this is 2, 4. That's right on the grid. And it's halfway up, 2, 4, 5. Again, your math lab is going to be able to do this very, very well. All right, let's try some others. Now, we're looking for strategy here. And what I see here, this equation, what kind of line will that be? Well, this was x equals a, which is a vertical line. So I can sketch that right in at 6. 1, 2, 3, 4, 5, 6. There's this line. And now I have to solve this, let's say, for y. And all I have to do there is put the y over on this side and put the 1 over there and change signs. So I transpose the 1. So my y-intercept is 1. And my slope is 6 1, 2, 3, 4, 5, 6, up 1. So I can see my point of intersection right away here. So my ordered pair for this one is going to be 6, 0. Now let's take a look at this one. And again, I'm going to have to do slope-intercept. And these numbers look a little bit big, so I'll probably have to use 2's again. So let me solve both of them for y. Put them in slope-intercept form. Now in the top equation, when I solve for y, it gives me some wild things. I believe the ones you're going to get are much easier than this. But our slope is a negative 2/5, and this is our y-intercept, which is 6 2/5 here. Here our slope is a negative 2/3, and our y-intercept is a 6 2/3. So let's see what this comes out like. All right, now for this one, it was pretty difficult. My best I could guesstimate here, it should intersect about there at 1,6. And graphing for something like this is really a challenge. But again, with MATLAB, you're not going to get these fractions. They're much easier than this. That would be a super difficult one to figure out. Now, as we do this next one, we're wondering, without graphing, determine the number of solutions of each system. The systems have a no solution or an infinite solution. So they're giving you a little hint here. So what strategy would you do, and again, without graphing? Well, I think what we'd want to do is put them in the slope-intercept form, compare our slopes, compare our y-intercepts. If the slopes are the same, but the y-intercepts are different, the lines will be parallel and there's no solution. If we end up with the same slope and the same y-intercept, then the lines are the same and there would be an infinite number of solutions. But as I say, they don't look like the same solution. Now this one is already in slope-intercept form. So we're going to solve this next one here. Negative 16y. I'm going to bring this x term over as a negative 4x plus 12. Now I'm going to divide everything by negative 16. So I get a positive y now. This is going to become a positive 1/4 x. And this is going to be a negative 3/4. So now this equation has worked out to be the same as the bottom. So the two equations are the same. So what do we have here? If we were to graph them, they would be one line on top of the other. So this would be an infinite number of solutions. Now let's solve for y here. This one is already in form. We're just going to switch it around. And this one, we're going to bring the y over to this side where it becomes a positive y. Y over to this side, positive y. X over to this side, negative x. And then plus 6. So what can we say now about our slopes? Well, both our slopes are a -1. And the y-intercepts, this one is 0, this one is 6. So there is no solution because the lines are parallel. Okay, you'll be doing some practice and quiz-mes on here, and it will be using your graphing skills.